Hello everyone, my name is Trần Vân Anh from Hanoi University of Mining and Geology, Vietnam. Today I'd like to talk about the radar theory. You already studied about the optical satellite images. So this is the other type of remote sensing. Its name is radar. This is the content of this lesson. Firstly, I will introduce some concepts. The reason for select that concept, for example, why we call it range and azimuth. Some terminologies like resolution, range and azimuth resolution, and continue with frequency and the relating between the frequency and wavelength. And I will explain about the single-look complex images and multi-look images. The distortion on the radar image will also be talked about that. And lastly is radar development history. Before go to the radar concept, I want to show about the electromagnetic spectrum. You can see the range in here is vary from very short wavelength to long wavelength. So before, when you study about the optical satellite images, it's vary from visible to infrared. So the wavelength is very short, from 0.4 micrometer to about 10 micrometers. But in microwave remote sensing or radar remote sensing, they use the wavelength between 1 millimeters to 1 meters. So it's very long wavelength. This is the concept of radars. Radar wave, an acronym derived from radio detecting and ranging, is a term used for range of wave with wavelength spanning from 1 millimeters to 1 meters that I showed you in the last slide. Satellite or aircraft equipped with radar sensor emit a source of energies and receive backscatter energies. Radar can be categorized into two types, active and passive, but in this lesson I just talk about the active sensor. In terms of image acquisition, there are two models, RAW and SAW, and I will explain after. You can see in the figures in the left, right, and in the left hand, you can see here the sensor has its own energies, not depend on visible light, and can work in the various weather conditions. Compared with the optical images, it captures visible light and it cannot penetrate the cloud or fog, as I will explain after. So in the right figures, you can see here, example with the position of satellite. If we want to acquire the data from one point in the Earth's surface, name is P, we have to know about some terminologies like range. The goal is slant range because with the radar, satellite is acquired the data in off nadir. Off nadir is look angle theta. It's not nadir, that means it's not perpendicular to the Earth's surface. So you have to remember about the slant range and look angle because between them we know about the how to acquire the data in different the look angles. This is two terminologies of radar. Name is RAW and SLAR. RAW is real aperture radar. A real aperture radar is a type of radar that uses an actually physical aperture for image formation. SLAR is a side-looking airborne radar. This is a side-looking imaging system. In reality, aircraft radar systems employ this type of imaging technique. You can see on the figures, with the aircraft, usually the sensor can be fixed on the right side or left side of aircraft, but actually with the satellite radar, it's also the sensor can be fixed on the side of the satellite. So the meaning of RA and SLA are almost the same. Here's the operation of radar system. The radar transmits a beam of pulse to the Earth's surface and collects the backscatter energies. I will explain about backscatter. You know about the radar antenna. It will send the signal like a beam of pulse to the Earth. So you will see in here the pulse like a black line curve. So it will hit to the house, to the tree, to the water and the other thing. And it creates many scatter. So one scatter will go back to the sensor. It will be called is the backscatter. So backscatter of house and backscatter of tree are different. So it will be safe in the receiver. Here's a comparison between radar and optical imaging system. Why I had to explain this one for you, because you already studied about the optical images. So now you had to know exactly the difference between radar and optical system. Firstly, the radar is independent of sun illumination, but optical are different. Optical is day operation. Because with the radar operates a transmitting radio wave and receive their reflection from the objects. So it is not dependent. It is not dependent on the visible light and can work in various weather conditions. But the optical imaging is rarely on capturing visible light reflected or emitted by objects, so it provides detailed color and visual information. You can see in two photos in here. In the first is the radar system and the other is the optical images. So the radar here has its own energies, send a signal as it receives the signal. But in this case of optical had the sensor in here and it receives the signal from the sun. You can see the sun in this color. The sun sends the light to the earth and reflection to the sensor of optical satellite. And the second difference between radar and optical is all-weather capability. That means the radars can penetrate through cloud, fog, and even Earth's surface to some extent, making it suitable for all-weather imaging and surface observation. But with the optical sensor, is weather limitation. That means it cannot be penetrated to the cloud or solid surface. The third thing is the radar has no effect of atmospheric constituents. Multi-temporal analysis is okay, but with optical, its effect of atmosphere constituent correction need. So the fourth thing is is radar sensitive to dielectric constant, like water contents or soil moisture or biomass, but with the optical sensor is sensitive to chemical constituents and chlorophyll or soil. About the sensitivity to surface roughness, the radar is very sensitive to the roughness, like sea state or topography. So that's why usually they apply the radar to create the elevation model. With the optical, is low sensitivity to surface roughness. So it's usually used for the land use land cover only. So with the sixth thing is it's sensitive to the target structures. So we can use for polarization of the radar satellite. So with the optical, it's no use polarimetry, but in case of the optical satellite, it can measure, it can acquire the data in different bands. But with the radar, there's only one band. One band, that means one wavelength can be used. So I will explain more detail about this in next slide. So with the accurate measures of distance, the radar can measure the distance very accurate. Because you see in last slide, I show about the slant range. Slant range, that means the distance between the sensor and one point in the earth. So with the optical system, it cannot measure the distance. And the last thing is subsurface penetration. That means it can penetrate to the earth like a thin of soil. But with the optical sensor, it cannot penetrate to the earth's soils on the earth. Its more terminology is in radar system. The first is the rain direction. Rain direction is the direction in which the radar looks horizontally, perpendicular to the flight path. Here is the flight path. And its direction of pulse energy transmission. As you see before, this is the pulse direction. It transmits the pulse like this one to this direction. So in radar, it is often used to indicate the distance from the radar to the target. In satellite imagery, it typically corresponds to the horizontal axis of the images, describing the variation in distance from the satellite station to the observed point on the route. So the blue light you can see is rain direction. And azimuth direction is the direction along the flight path. Here is flight path. So usually azimuth and rains perpendicular to each other. Another is rain resolution. You study about the optical system. The resolution usually size of pixel. So the size of pixel usually is square. But with the resolution of radar system is different. It's divided in two types, range and azimuth. So we call it range resolution and azimuth resolution. With range resolution, the signal is transmitted in the form of pulse. The time between two transmission and reception instant can be measured. The signal is assigned to geographical location based on real-time measurement. T1, T2, T3, and T4. You can see in here, for example, the Earth's surface is flat like this one, but there's some point in here we need to acquire. And the pulse transmit from the sensor to the Earth. It will hit to each point in different time. That means the sensor sends a signal to the first point, it will have the T1, and the second is T2, and the third is T3, and the fourth is T4. That means when the signal hit to the Earth's surface, it will have to come back to the sensor. That means backscatter will come back to the sensor at different time. So the same with T1, T2, T3, and T4 is will be come back with the same time. That means the pulse will have the time of time. That means T1 multiplied to 2. So when it comes back to the sensor, it will be safe in one signal of 1 point. So the resolution, range resolution, that means the time is have to separate it. That means the time to first, second, third, and fourth when come back to the sensor, it will be separated. If it cannot separate it, that means is there no resolution between 2 points. More explanation about range resolution. In radar system, range resolution is determined by pulse width of the radar's signal. A shorter pulse width results in better range resolution because it allows the radar to distinguish between closely spaced objects. Mathematically, range resolution is inversely proportional to the pulse width of the radar signal. You can see it here with the equation show about the range resolution. An example of two objects A and B. So in case of A and B, with the distance in range, like the first figure is D, you can see the pulse sent to the Earth hit to A and then hit to B and it come back. If the distance of the pulse name is L, the L is short, is better than the L is long. You can see in the second photo, the second figure in the lower of the slide, when the pulse sent to the Earth's surface, it will hit to A and come back, and then it will hit to B and come back. But L is long, so when the signals go back from the A and the B signals go back, the top of the signals from B and the end of signal from A is nearly very close to each other, and it can be connect to each other and come back to the sensor. That means it's very close to each other, and then when it comes back, it will be saved to the 1 point. That means it cannot resolute to each other. So that means the sensor understands that 2 points A and B is 1. Here an example of range resolution help you to understand more clearly about the range resolution. For example, we have the distance of the pulse is 300 meters. That means L is 300 meters. And we want to detect two objects on the airspace, like two airplanes. But two airplanes in the first figures is half the distance between two airplanes is 100 meters. When we send the pulse with the distance of the pulse is 300 meters to object airplane, it will send signals and receive the signal back to here, and you can see the cyan color when this send and receive the signal. The cyan color is be connected, and when it's come back, it's like a one signal. But in the second figures, the distance of the pulse is still 300 meters, but now the distance between two objects is 200 meters. When the signal sent to the airplane and it's come back with the cyan color, you see, it's separated between two signals, and then we can detect two airplanes. It's not one, but with the first figures, that means the sensor understands that there's only one airplane, but in the second figures, it can separate it and understand that there are two airplanes in airspace. More explain about the slant range. The slant range, it is a plane along the radar beam where the image is constructed. Why do I have to explain about this? Because you have just studied about the range resolution. The range resolution shows the pixel of the object can be saved to the images. So, for example, in case of this point, one is be saved to the sensor as well as this one, because you imagine that the signals can be sent like a curve, the black curve like this one. So when the signal saved in the slant range direction, it will be compressed in horizontally like this one. So here an example of the images acquired by the radar satellite. So everything like compresses, and it look like something we pulled. It look very longer than the natural thing. More terminology is called ground range. Last slide you have just studied about the slant range, right? So slant range images is decompressed like this one. So the pixel is rectangles and it's be distorted. So when we want to work with the radar images, we have to transform from slant range to ground range. That means move from slant range to the ground. So the equation for transform from slant range to ground range is in the left hand. The ground range equal with slant range multiplied with sine of look angle. Look angle, that means this one. So the look angles is not the constant. It varies from near range to far range. So the pixel, that means it's also be distorted, different from near range to far range, as I will explain after. Now we continue with the azimuth resolution. As you have just studied about the range resolution, and now the azimuth resolution is follow the azimuth direction. That means the flight direction. So azimuth resolution refers to the ability of radar system or sensor to distinguish between two separated targets or features in the azimuth dimension. It measures the smallest angular separation between two targets or features that can be solved as distinct entities in the radar sensor field of view. So you can see in here azimuth direction in this follow the arrow. So azimuth, we name it AR, depend on the side of antenna, because with the sensor it usually is the antenna to send the beam to their surface. So the azimuth resolution depend on the AR. AR is the antenna beam width multiplied with slant range, where antenna beam width refers to the angular with the radar's antenna beam, and slant range you already know the distance between the radar and the target. And antenna beam width equal with lambda divided L. Lambda is the wavelength of the radar signals, and L is the physical size of antenna. So lastly, AR, that means the azimuth resolution equal lambda multiplied with R, that means slant range, divided to L. You know about the distance between the satellite to the point to the Earth. That means slant range is very long, very long. For example, in some case, R is 800 kilometers, some is 500 kilometers or 700 with the spaceborne radar. And here an example. For example, L, that means the side of antenna is about 10 meters. Comparing with the slant range, R is approximately 800 kilometers, and lambda with C-band is 5.6 centimeters. So the resolution will be 4.4 kilometers. It's very big. And the 4.4 kilometers, that means 4,400 meters for one side of pixel. That means it's very rough, and it's very difficult to recognize the object on the Earth. So this is the azimuth resolution of real aperture radar. Okay, you have just studied about the azimuth resolution with the long range slant range is about 800 kilometers. The resolution is about 4.4 kilometers, so it's very low. That means real aperture radar. So to overcome the bad resolution in azimuth direction, synthetic aperture radar (SAR) is created. So synthetic aperture radar (SAR) is a type of radar system used to create high-resolution images of the Earth's surfaces. It achieves this by utilizing the motion of the radar antenna to synthesize the larger effective aperture. So imagine that this is one position of the satellite. It will send the signal to the Earth and receive the signal backscattered. So it moves to the second place. It will also do the same, and then it moves from the first and the end position. It will create the synthesized longer antenna. If the longer antenna will create the higher accuracy in azimuth direction. That means the idea of synthetic aperture radar. Now continue with the frequency and wavelength. In physics, frequency in the context of radar system or electromagnetic wave in general refer to the number of oscillation or circle of the wave that occur in a unit of the time. It is typically measured in Hertz, where 1 Hertz represents 1 circle per second. You can see in here the equation relating between the lambda and f, that means the wavelength and frequency. And you can see in this equation, lambda and f is inversely relationship. So in this case, c is the speed of electromagnetic radiation equivalent to the speed of light is approximately about 3 multiplied 10 exponent 8 meters. And lambda is the wavelength and f is frequency. So in case of high frequency, that means high frequency, the wavelength is shorter. Shorter wavelength, higher frequency. And opposite is lower frequency, is longer wavelength. So the wavelength will decide which band the radar satellite acquire the data. So it's related to the next table. You will see the information of radar band. Here, the relationship between the wavelength, frequency, and band. As you know about the optical images, with optical radar satellite, it acquires the data in different bands and different band with different wavelength. But in the case of radar, one satellite only acquires the data in one wavelength. For example, in case of Sentinel-1 satellite, it will acquire the data from 3.5 centimeters in C-band. So the band of radar images, its name is the characters, is not number like an optical system. In the optical system, you know, before, for example, in case of Landsat or Spot or Sentinel-2, it has some different bands. For example, the band name is 1, 2, 3, 4, 5. It is like a red, green, blue, near infrared, something like that. But in case of radar, the name is PLC, X, KU, K, and KA. So it depends on the wavelength as well, have the different frequency. You can see the column in here is wavelength in centimeters and frequency in gigahertz. So longer wavelength, lower frequency, but shorter wavelength, higher frequency. In case of C-band, 3.75 to 7.5, the frequency is about from 4 to 8 gigahertz. But in case of KA, the wavelength is about 0.75 to 1.11. So the frequency is much more bigger. It's about 27 to 40 gigahertz. Polarization. As you know, with the optical system, they acquire the data in different bands. But in case of radar, it acquires only one band, that means one wavelength. So it is very difficult to recognize the object if we use only one band. That means just only a black and white. So the polarization is created to overcome this. So what is polarization? Polarization refers to the orientation of the electromagnetic wave as they are transmitted and received by the radar system. So electromagnetic signals are transmitted by certain plane. That means they're divided into two planes, electric and magnetic. Electric current is vertical and magnetic is horizontal. The plane of the oscillation is often represented in horizontal coordinate h and vertical coordinate v direction. So if the electromagnetic transmit into the vertical direction and receive the signal all in the vertical direction, is called VV. And if the signal transmit follow the magnetic, that means horizontal direction, and receive the signal also in horizontal direction, is called HH. And if the VV and HH happen as well, called the co-polarized or like polarized. In case if the signal transmit in V direction, but if it receive in horizontal direction, it called it VH. If the signals transmit in the horizontal direction and receive in vertical direction, is called HV. In case of HV or VH transmit and receive, they call it a cross-polarized or cross-polar. So different polarization is well easier to recognize the object, especially the vegetation. For example, in this case of a rice field, with the vertical wave, it interacted with the vertical structure of tree in here, but horizontal polarization wave will penetrate through the tree canopy. So different polarization is well can recognize different type of vegetation, also different height of the tree also. Here an example of combination of the different polarization. So in this case, we use three polarization for combination. The first one is HH polarization. The second is VV polarization. And the third one is HV polarization. When we want to make the RGB images, we just assign the color for each polarization. For example, HS we assign the red color, VV assign the green color, and HV assign the blue color. When do the combination of three polarization, we got the images like this one. And the vegetation and the other object when easy to recognize. You see in here in some arrow in here, for example, with the yellow or violet or green or white, that means different type of vegetation on the field. So this is not so bad, right? So you can see here, you can use these images for object classification or make the land use land cover or something like this. Next is the factor influencing radar backscatter. Why do we have to understand about the influencing radar backscatter? Because we understand about the influencing backscatter, we can select the right band for our research. For example, in case of X band, C band, or L band, which one is better to select for the land use land cover or detect the something underground or something like that? So in this example, we use three bands for comparing X, C, and L. So the wavelength is depend on the frequency, So with three types of object: vegetation, dry alluvium, and dry snow ice. So with the first, you can see in here, with the first band, X band, it's just only on the top of the tree with the vegetation. With X band in the vegetation, it's just the heat to the top of the tree and penetrate the first layer of leaf. If X band is lambda equal 3 centimeters. Information content in the image related to topmost layer, which means the tree top. In the case of using L band, lambda equals 23 centimeters. Radiation can penetrate to the leaf and to the branch. Then the information content in the images will relate to branch and even trunk of the tree. And also in the other, like a C band, it can go through the first and the second layer. It may be reflected and scattered inside the first and the second layer of the tree and go back to the center. So that is example of vegetation. The other example is dry alluvium. So also the same with X, C, and L. With X band, it just go to the top of alluvium. So it's go to here and go back. The second, with C band, about 5 to 6 centimeters, and it go to the thin layers of dry alluvium and go back. With L band, it penetrates deeper and it goes longer inside the dry alluvium. With the other object, it dry snow ice. You can see in here, with the dry snow ice, X band, the signal go to the top of dry snow ice and go back. With C band, it also penetrates in the thin layer of snow ice, and with L band, it go more further to inside the snow ice. And then we concluded that the penetration depth is depend on the wavelength. So the roughness of object is also a factor to consider. The penetration ability of wave increase with the longer wavelength. Penetration ability is only related to the moisture of the object. So extremely high frequency wave cannot penetrate water effectively, only a few millimeters. Here an example of radar images at different wavelengths, X, L, and P. X is shortest, it's about 3 centimeters, L about 23 centimeters, and P is larger, 30. So its shortest wavelength is easily can detect a small thing. So it's more detailed when using the shortest wavelength. But it cannot, as I saw before, it cannot penetrate to the canopy. So it easily detects something on the top. So you can see the color of each images will be different, because the detection of the object also in different layer. So in this, for example, in this area maybe it's related to vegetation. So with this color is darker. So because it just only on the top. But with L band, it goes further inside the canopy of tree. So maybe it hit to the trunk or a branch, so it go back. So the color of this in this area, you can see in this area, and this area. So in this, the color is brighter, and the other with P band, the wavelength maybe is greater than 30 centimeters, so it go further inside the vegetation. Maybe it hit to the ground and go back. So the color here is very bright in the same place with this and this and this. So you see in the area with the vegetation in this place, and this one, and this one, with different wavelength, that means different band, it will have different color. One thing we need to know about the radar signal is speakers. Speaker noise is the creation of the small range caused by the addition or subtraction of pair of signals. You can see in here when two pair of signals, it will create the constructive interference or destructive interference. It will create very white or very black in the images. So if there in the images have many black and white close to each other, it will to become a noise. They call it speaker noise. Or speaker noise is multiplicative noise caused by a characteristic of the wave. So with the speaker, we need to remove it. So with the noise, we have to remove. And also the same with the optical system. They also use some different ways to remove the noise. So in case of radar, also a little bit the same. But we usually use some different type of speaker removing, like they call it adaptive filter. So adaptive filter, that means it still remove the noise, but it keep the edge, preserve the edge. So some example of the filtering method is called Lee or Quan Frost or adaptive leaf or something like this. You will see on the software. Now I want to say about the single look complex images. When you study about the optical images, you know about the value of optical images is just only a number. But in the case of using radar images, the raw data is called a single look complex images. So with the single look complex images, you can understand it can divide it in two parts. That means single look and complex images. So what is a single look? The term of single look refers to the fact that the each pixel in the images corresponds to a single radar pulse or look at the ground. In the other words, no averaging or combining of multiple radar pulses is performed for each pixel. But the complex data, what is a complex data? In sub-processing, the received radar signal is typically represented in complex form. So complex form, it contains both magnitude and phase information. The single look complex images retain this complex representation. So here is the illustration of about the complex data. For example, you have one point, that means one pixel. we want to know the value of one point in the complex data. That means you have to select this point in two axes. That means A in real and B in imaginary. They call it real and imaginary in complex data. So, for example, in case of 1 pixel, it will show in Z. Z equal A, that means real part, plus with IB, that means imaginary part. So in imaginary part, we have I, that means I squared equal -1. That means it's complex. It's the imaginary unit in complex. So this 1 pixel have one value. That means the value is divided in two parts, real and imaginary. Just remember that. Another terminology is multi-looking. Multi-looking, that means multiple single-look complex images covering the same area are averaged together. So each pixel in the resulting multi-looking images is computed by the average of the corresponding pixel from the multiple single-look complex images. So you will see in here, for example, in one place in the earth, when you look one time, you call it one look. That means one single look. But when you move the satellite to the other position, it will also look at one place on the earth and the other also the same. So when many positions of satellites will look on the one place on the earth, so it creates the multi-looking. So multi-looking, that means to averaging many looks. So averaging the signal of one pixel, but in many looks. That means they call it multi-looking. So multi-looking is computed by using equation I. That means this measure intensity. So measure intensity equal with seen reflectively. So multiply with V, that means speaker noise, L is number of looks. So in the equation here show the I equals sigma. So variation of I equals sigma divided to L. So when you see this equation, you can understand about reducing noise if the L increases. So spectral filtering consists of assessing sigma from I by reducing the variation of I, and therefore increasing the equivalent number of looks is better to reduce the noise. The features of radar is image distortion. Why is have distortion? Because the radar acquired the data is not nadir, but it off nadir angle. So that's why it usually create the distortion. So there are three distortions. That means when the object on the earth had the high elevation, it will create some distortion. The first thing is layover. What is layover? Layover often occurs when the incident angle reach the surface with the elevated topography such as mountain or tall buildings. Taller objects tend to fall back forward to the antenna. example, you can see in here we have the pyramid. The pyramid have the top is B, A and C is the foot. If in case the optical system when acquire the data, the A will be acquired in the first, the B in the second, and the C in the last, right? That means on the images you can see from the left to right is A, B, and C. But in case of radar, it sends a signal to the Earth, which signals hit to the object. First it will go back ahead. So when the signal go to the pyramid A, B, and C, it hit to the top first, and then it hit to the A, the foot A, and then it hit to the foot C. When it acquires the data, it will become B, A, and C. That means the B tend to fold, and it's become ahead before acquire the A. So that's why you can see the images look very different in the nature. So it's not like a pyramid. Now it can be seen B, A, and C. So it called it layover. So it's one type of distortion. The next distortion is called foreshortening. Foreshortening also occurs in case where the incident angle reach terrain with convex or concave features. For example, it still use the pyramid A, B, and C, but in this case, the pyramid is not high like before, it's lower. So when the signal hit to the Earth's surface, it will hit to A, B, and C. But A and B is very close to each other. So when the images be acquired, it will A, B, and C from the left to right. But A and B is very close. So for example, in the real, the AB distance will, for example, 200 meters. But in case when it's acquired, maybe it compresses, become only 20 meters. So it's be distorted. That means it's in this case still follow the order A, B, and C, but the distance between A and B be distorted and smaller, much more smaller than the real one. So it's called as foreshortening. The last distortion, they call it shadow. Shadow occurs in the relation to the incident angle and terrain. High terrain, that means mountain or tall building, create shadow behind objects. No signal reflection from that area. For example, in case still using the pyramid like this one, so we have the foot, the top, and the foot. But in this area, that means the foot of the pyramid in the right side, the signal sent to the top, but it cannot go through here to hit to the foot of the right side of the pyramid. That means the area be covered, cannot see. So the area cannot see, we call it the shadow. Here an example of distortion. You can see some mountain road. So the first thing is layover. You can see the layover, the top of the mountain is be fold to the left when the look direction from left to right. So you see here some top of the mountain. So you can see it's like a wave. So you can see in here is recognize it as the top of mountain, and this is the foot of the mountain. Look very different, so very difficult to recognize. And the other foreshortening, you can see the foreshortening like this one is like it create very short from the top and the foot of the mountain. It's like this foreshortening. And shadow is easy to recognize. That means it creates the black areas behind the mountain. Here also the shadow. This is image processing. So you can see in here from left to right is the processing of SAR data. The raw data is called single look, slant range complex images. It looks very different with the reality and difficult to recognize the thing on the images. So for example, if you want to interpret something on the image, you have to understand what it is. So to do that, we have to step by step do some correction. So firstly, we create the multi-looking. Multi-look images called multi-look ground range detected. So with the multi-look ground range detected, we just create like average many single look conflict to also reduce the noise and create the images like this one. So in this images, you see it's different with the large image I show in the example. In this case, the image is in look from the right to left, because you see in here the top of mountain is fold on the right side. So in these images, you can a little bit understand about that. For example, here understand that is the mountain, but still cannot interpret it. So next we have to draw reference. That means code is draw coded with something like a draw coded with ellipsoid. When we are draw coded with ellipsoid, the image will rotate and move to the draw reference position. So in these images, you can understand where it is in a coordinate system. But the mountain still layover or foreshortening, you still cannot recognize. If we want to interpret the object, we have to use more correction. That means using DEM, digital elevation model correction. That means DEM will remove the distortion like foreshortening or layover or layover, foreshortening, and shadow. So using DEM, we have the large images. So this image we can use for some purpose. The emergence of radar. This is like a history of development of the radar satellite. Actually, the radar satellite is booming from 1992. It had from EIS-1 from ESA. So continue with EIS-2 is still in C-band. So the others is also of ESA is continue in Envisage ASA, and then now is Sentinel-1A and 1B in different years. So you can see in here multi-frequency with X, C, and L band. With C band is the typically with the some satellite from ESA, as I have just explained to you. But the other you can know about L band. The L band is GIS-1 from Japan. GIS-1 was launched in 1992, and then it continued with the Alert Panzer when GIS-1 is terminated. So Alert Panzer is Alert Panzer 1 and Alert Panzer 2. Alert Panzer 1 now is terminated, and then is Alert Panzer 2, and now it's had NISA. And the other is X-band. X-band is shorter wavelength, has Cosmos SkyMed. It is launched from 2008, and then Terasa X and Tandem X, ComSat 3 and Cosmos SkyMed, new Cosmos SkyMed in 2017. So you see in here is I just mentioned some different satellite using C and L and X band, but actually have the other band also P band or the other band, but in this case we just use in some kind of the data image in C, L, and X for Earth observation. That's why I select this type of satellite to show you. Here an example of Sentinel-1. Sentinel-1 is a typical of C-band satellite from ESA. Why I select this one to introduce to you? Because it is free. It's free data, and it's also very good. For example, of using C-band for detect something on the Earth using this such kind of images. So Sentinel-1A was launched in April 2014, and Sentinel-1B was launched in 2016 April, and up to 2021 Sentinel-1B was terminated. So continued they will launch Sentinel-1C and 1D. So the mission object is land monitoring of forest, water, soil, and agriculture, with oceans monitoring a state of dynamic of ocean and coastal zone, and climate long-term monitoring to understand the feedback of interaction of the climate change, like land cover, forest covers, land subsidence and sea ice sheet and glacier, etc. So it is C-band, that means about 3 centimeters. So its repeat circle is 12 days, but we have 1A and 1B in the archive. Maybe you can have the image only 6-day circle because 1A and 1B. And multi-mode resolution from 5 to 20 meters, swath width up to from 250 to 400 kilometers, and it's free access. That's why this is an example that I want to show you. and pre-processing tool and analysis ready available to you. For example, you can use Snap or use free cloud software like using the Google Earth engine to process such kind of data. It's very good. The other example is Alert Panza. Alert Panza is two types of Alert Panza. Alert Panza 1 was launched in 2006, and the other is Alert Panza 2 was launched in 2014. The Alert Panza 1 is terminated in 2011. So now you can free download Alert Panza 1 from website, and Alert Panza 2 ground range detected you can download free, but it's limited some because it has the many type of resolution, but you just can select or download the maybe 30 meter resolution, and it's global free mosaic data from 2007, 2008, 2009, 2010, 2015, 16, and 17, etc. So the mission objective of the Alert Panza is also monitoring, including solid earth research, or also monitoring for sustainable earth in forest, cryosphere and sea ice, natural resources like agriculture, ocean monitoring, and resources and technology development for the future Earth remote sensing. It's L-band. L-band is about 23.5 centimeters with the Alert Panza, and the repeat circle is 14 days multi-mode resolution from 3 to 10 meters swath width up to 70 kilometers, and a free access of mosaic data at 25 meter resolution. And here's the reference that I make this lesson. You can access this website or that data to collect more the information about this. Thank you for your attention.